There's evidence something massive is pulling on objects at the edge of our solar system. Not a star, not a black hole, a planet large enough to reshape our map of the Sun's neighborhood. Scientists call it Planet 9, and it may explain the strange clustering of distant orbits. But the biggest question remains: where is it hiding? Subscribe if you enjoy mysteries backed by real science. Past Neptune, the solar system doesn't end, it transforms into something else entirely. Neptune orbits 4.5 billion kilometers from the Sun, 30 times Earth's distance. Most textbooks mark this as the boundary, the edge of our cosmic neighborhood. But travel 20 times further out, and you enter a region so dark, so cold, so empty, that a planet 10 times Earth's mass could hide there for 4 billion years completely undetected. The Sun, at that distance, provides 1/10,000th the light it gives Earth. High noon feels like deep twilight. Temperatures approach absolute zero, that theoretical bottom where atoms nearly stop moving. Light takes 13 hours to reach here from Earth. Send a message and it arrives tomorrow. Wait for a reply and you've aged 2 days just exchanging pleasantries. The delays aren't inconvenient, they're existential. But something strange happens out there in that void. Objects don't move right. Small rocky bodies, trans-Neptunian objects, scientists call them, follow orbits that curve in ways they shouldn't. Not toward the Sun, which would make sense sideways, like invisible hands are pulling them off course, bending their paths toward something massive that gives off no light. This is where Planet 9 might exist. Astronomers Michael Brown and Konstantin Batygin proposed it in 2016 after running computer models. 5 to 10 times Earth's mass, orbiting somewhere between 400 and 800 astronomical units from the Sunday. An astronomical unit equals Earth's distance to the Sun, so we're talking distances that make Neptune look close. At those ranges, searching for a dark object becomes like hunting for one specific grain of black sand scattered across Australia at midnight without a flashlight. Nobody has seen Planet 9 directly. The evidence is mathematical, inferential. Gravitational fingerprints left on smaller objects whose orbits shouldn't align the way they do unless something massive is shepherding them. It's detective work at cosmic scale, finding the monster by its footprints while the creature itself remains invisible. Our solar system is 99% unexplored void. We've mapped the inner planets because they're close and bright. We've studied Jupiter and Saturn because they're enormous. But the true outer reaches, where the Sun's warmth fades and darkness takes over, remain as unknown now as they were 400 years ago. We've just gotten better at pretending otherwise. We can photograph galaxies 13 billion light-years away. We can detect gravitational waves from colliding black holes. We can measure radiation left over from the Big Bang. But we can't answer a simpler question that hits closer to home. How many planets orbit our Sun? We're still counting, still discovering we might have missed something huge. The darkness doesn't start at the nearest star system, 4 light-years away. It begins right here, just past Neptune, in our own backyard. And in that darkness, something might be circling. 1846. Astronomers noticed Uranus wobbling in its orbit, moving wrong, pulled by something invisible. 2 mathematicians, Urbain Le Verrier and John Couch Adams, ran calculations predicting where this mystery object should be. They pointed telescopes at that specific patch of sky and found Neptune within 1 degree of the predicted position. A planet discovered by math before it was seen by human eyes. That was 178 years ago. Now it's happening again. Something out past Neptune is pulling on objects, bending their orbits in patterns that shouldn't exist unless something massive is hiding in the dark. The story starts with trans-Neptunian objects, rocky chunks of ice and stone left over from the solar system's formation, orbiting in the region beyond Neptune. Most follow predictable elliptical paths, but in 2003, astronomers discovered Sedna, a dwarf planet with the strangest orbit anyone had seen. Its closest approach to the Sun still kept it 76 astronomical units out, never coming anywhere near Neptune. Something had pulled Sedna into that distant orbit and left it there. Then came more discoveries, objects with orbits that shared something bizarre. They all swung out in roughly the same direction. Their orbital planes aligned within 30 degrees of each other, and their closest approach to the Sun, what astronomers call perihelion, clustered around the same angle. One weird orbit might be coincidence, two could be chance, but 6 objects, all with similar orbital characteristics, all pointing the same direction? That's a pattern, and patterns in nature usually mean something's causing them. Chad Trujillo and Scott Shepard published a paper in 2014 pointing out these orbital alignments. They suggested something massive must be out there, gravitationally herding these smaller objects into similar paths. But they didn't have enough data to predict where this massive object might be or how big it needed to be. Michael Brown and Konstantin Batygin took the idea further. Brown had discovered Eris, the dwarf planet whose existence triggered Pluto's demotion, so he knew the outer solar system better than most. He teamed up with Batygin, a theoretical astrophysicist who specialized in planetary dynamics. They spent months running computer simulations, testing different scenarios. Could random chance explain the aligned orbits? Could Neptune's gravity be responsible? Could a scattered disk of smaller objects create this pattern? Every conventional explanation failed. The simulations kept pointing toward the same conclusion: a planet 5 to 10 times Earth's mass, orbiting at 400 to 800 astronomical units, tilted about 30 degrees relative to the other planets. That configuration, and only that configuration, produced orbital alignments matching what telescopes were seeing. The probability of these alignments happening by random chance was roughly 3 in 10,000. Possible, but unlikely enough that betting against it seemed foolish. Brown and Batygin published their findings in January 2016. The paper hit astronomy like a thunderclap. Here was serious mathematical evidence that the solar system contained a 9th planet, a massive world we'd somehow never noticed, despite 4 centuries of increasingly sophisticated observations. But the evidence isn't the planet itself. Nobody's photographed Planet 9. Nobody's measured its light, or analyzed its spectrum, or detected its heat signature. The evidence is how other things move. Small rocks billions of kilometers away, following paths that bend wrong unless something invisible is pulling them. It's like watching leaves rustle in patterns across an empty field and concluding something massive must be walking through, even though you never see the creature itself. Think about what it takes to find something by its gravitational influence alone. You need objects close enough to that influence to show measurable effects. You need to track those objects long enough to map their full orbits, which can take decades or centuries. You need computer models sophisticated enough to simulate what different hidden masses would do, and you need enough observed objects to distinguish pattern from noise. We only started finding trans-Neptunian objects in significant numbers in the 1990s, when telescope technology and detection methods improved enough to spot things that dim and distant. The aligned orbits kept multiplying as astronomers searched specifically for more trans-Neptunian objects. By 2016, the count had grown to 14 objects with similar orbital characteristics. By 2020, more than 20. Each new discovery refined the mathematical models, narrowing down where Planet 9 should be and how massive it must be to produce the observed effects. But finding the planet itself proved extraordinarily difficult. Brown and Batygin could predict a region of sky roughly 20 degrees across where Planet 9 might currently be located. 20 degrees sounds precise until you realize that's 400 times the apparent size of the full moon. And Planet 9, if it exists, would appear as a faint dot, easily lost among background stars. Its visual magnitude would be somewhere around 22 or 23, meaning you'd need a fairly large telescope and long exposure times just to detect it, moving so slowly across the sky that you'd need months or years between observations to confirm it wasn't just a distant star. Teams started searching. The Subaru telescope dedicated observation time to scanning the predicted region. Other groups analyzed archival images from sky surveys, looking for faint objects that moved slightly between photographs taken years apart. It's tedious work, examining millions of data points, most of which turn out to be background stars, or instrumental noise, or cosmic rays hitting the detector. Then, in 2024, researchers analyzing data from 2 defunct infrared satellites found something remarkable. The satellites, one launched in 1983 and another in 2006, had surveyed the sky in infrared wavelengths, detecting heat signatures from celestial objects. The data was old, stored in archives, but it covered vast areas of sky, including the region where Planet 9 might be hiding. The research team filtered through more than 2 million potential candidates. Most were known stars or asteroids. A faint infrared source that appeared in both satellite datasets, separated by 23 years. And between those 2 observations, it had moved. Not much, just a fraction of a degree. But the motion matched what Planet 9's orbital models predicted almost perfectly. 2 data points, 2 faint smudges of infrared light captured by satellites that stopped working years ago. That's the evidence. It sounds absurdly thin, laughably insufficient. But consider what it took to find even this much. 2 million candidates filtered down to 1. 23 years between observations showing consistent motion. And that motion matching theoretical predictions to within the margin of error. It's like trying to find one specific atom in all of Earth's haystacks. You're looking for something that doesn't emit light, barely reflects any, moves incredibly slowly, and hides in a region of sky larger than 400 full moons. And somehow, buried in decades-old satellite data, someone found 2 pixels that might be it. 2 moments frozen in time, 23 years apart, showing an object drifting through the darkness exactly where the math said it should be. The astronomical community remains cautiously skeptical. 2 observations aren't enough to confirm a planet. You need continuous tracking, multiple images showing the object moving along a predictable path, spectral analysis to understand its composition, brightness measurements to calculate its size. All of that requires finding the object again with current telescopes, locking onto it, following it for months or years. And so far, nobody's managed that follow-up confirmation. But the mathematical case keeps strengthening. In 2021, astronomers found more distant trans-Neptunian objects with orbits that fit the Planet 9 hypothesis. Computer simulations by different teams using different methods kept arriving at similar conclusions. Something with 5 to 10 Earth masses, orbiting between 400 and 800 astronomical units, tilted 30 degrees. The models were converging on the same answer from multiple independent approaches. Alternative explanations started looking increasingly strained. Could the orbital alignments be observational bias, artifacts of where and when astronomers happened to look? Multiple teams checked and found the bias couldn't explain the full pattern. Could a scattered disk of smaller objects collectively create enough gravity? The math said no. You'd need implausibly large amounts of mass distributed just right. Could Neptune's resonances be responsible? Again, no. The orbits were too distant for Neptune's influence to dominate. Every alternative required special pleading, improbable coincidences, or physics that didn't quite work out. The Planet 9 hypothesis, meanwhile, explained everything with a single massive object whose existence wouldn't violate any known laws. Occam's razor, that principle suggesting the simplest explanation is usually correct, pointed toward one answer: a planet, hiding, waiting to be found. And here's what makes the detective story genuinely strange. We're not looking for something exotic. Not a black hole, not dark matter, not some weird new physics, just a planet. A regular, mundane planetary body, like the ones we've known about for centuries. Except this one happens to be so far away, so dim, so isolated that it escaped detection until telescopes and computers became sophisticated enough to spot its gravitational fingerprints on smaller objects. The ghost in the dark leaves footprints everywhere. Dozens of trans-Neptunian objects, all bent the wrong way, all aligned in patterns that scream something massive is here. The math works. The models converge. The two infrared detections from decades ago line up with predictions. Everything points to the same conclusion, and yet we still haven't seen the planet itself, just its shadow, just the spaces it bends around itself, just the way things move when it passes nearby. 4.5 billion years ago, when the solar system was young and chaotic, something went catastrophically wrong. The planet that would become Planet 9, if it exists, was born closer to the Sunday. Maybe it formed near Jupiter or Saturn, one of several large planetary bodies competing for the same orbital space. The early solar system was crowded, violent, unstable. Planets migrated, orbits shifted, gravitational interactions grew increasingly complex. Then came the encounter. Maybe Planet 9 passed too close to Jupiter, the solar system's gravitational heavyweight, 2.5 times more massive than all other planets combined. Or maybe Saturn was responsible. Either way, the interaction was brutal. Planet 9 got flung outward like a stone from a slingshot, accelerating to escape velocity, headed for interstellar space and permanent exile. But it didn't quite make it. The Sun's gravity, weakened by distance but still present, caught Planet 9 at the last possible moment. Instead of escaping into the void between stars, the planet entered an extremely elongated orbit, captured but not contained, bound but barely, trapped in the slowest orbit imaginable, taking somewhere between 10,000 and 20,000 years to complete a single lap around the Sunday. All of recorded human history, every empire and invention and war and discovery, happened during roughly half of one orbital period for Planet 9. When this planet was last at its closest approach to the Sun, humans were hunter-gatherers scratching pictures on cave walls. Civilization didn't exist, writing didn't exist, agriculture didn't exist. The planet won't return to that closest point until sometime around the year 12,000. Everything we think of as human history, from the first cities to the internet, exists within one season of Planet 9's year. The planet has orbited the Sun only about 200,000 times since dinosaurs walked Earth. That sounds like a lot until you consider Earth has circled 4.5 billion times in the same period. Planet 9's sense of time operates on a scale so removed from human experience that we don't have good metaphors for it. Each orbit outlasts dynasties, languages, entire civilizations. The planet moves through space at roughly 1 kilometer per second, fast by human standards but glacially slow for an astronomical object. It would take months just to watch it drift across the width of the full moon. Right now, wherever Planet 9 currently sits in its orbit, it exists in conditions no human has ever experienced or can truly imagine. The Sun from that distance appears as just a bright star, brighter than any other, but no longer a disk, no longer warm, no longer remotely close. It provides about 1/10,000th the illumination Earth receives. Stand on Planet 9's surface, and high noon would feel like the last moments of twilight on Earth, that brief window after sunset, when you can still see shapes but colors have faded to shades of gray. The temperature hovers around -230 degrees Celsius, approaching the theoretical minimum where molecular motion nearly stops. Any atmosphere the planet might have had long ago froze solid and snowed out onto the surface. Nitrogen, methane, carbon dioxide, all the gases that make up planetary atmospheres, exist there only as ice. The surface could be covered in methane snowdrifts, frozen nitrogen lakes, ammonia frost coating every exposed surface. Or maybe the planet has no solid surface at all, just a ball of hydrogen and helium like a miniature Neptune, wrapped in layers of methane ice clouds that never move because there's no sunlight to drive weather patterns. Nothing happens there. No wind, because that requires temperature differences and energy from a nearby star. No geological activity, because the planet's interior likely cooled billions of years ago in that frozen exile. No auroras, because solar wind particles barely reach that far out. Just stillness, silence. Darkness so complete, it makes Earth's deepest caves look bright by comparison. If you stood on that world and looked up, you'd see stars exactly as clear as they appear from anywhere else in space. But the familiar constellations would be subtly wrong, shifted by the extreme distance from their appearance, as seen from Earth. And the loneliness, this is what strikes hardest about Planet Nine's existence, if it exists. The isolation isn't just physical distance, it's existential distance. Light from Earth takes 13 hours to arrive there. A simple conversation would require 52 hours for a back-and-forth exchange. If someone on Planet 9 sent you a message saying "I love you," your response wouldn't reach them until 2.5 days later. By then, everything could have changed. Relationships would die in the lag time. Friendships would be impossible. Any connection to the inner solar system would feel less like communication and more like leaving messages for the distant future, hoping someone eventually hears them. The planet belongs to the solar system only technically. It's gravitationally bound to the sun, yes, but barely. It occupies the vast middle ground between bound and free, between belonging and exile, between home and interstellar space. Move Planet 9 just slightly further out and the sun's gravity would lose its grip entirely. The planet would drift away, joining the billions of rogue planets astronomers now believe wander the galaxy untethered to any star. Planet 9 exists on that knife's edge, permanently on the verge of leaving but never quite escaping. And it's been there the entire age of the solar system, 4.5 billion years circling in that outer darkness, completing maybe 225 million orbits total. Earth has been around for the same duration but has completed more than 4 billion laps. The inner planets have lived thousands of lifetimes, while Planet 9 completes one. It's the Methuselah of orbital periods, ancient and patient and impossibly slow. Think about what the planet has witnessed, if something without eyes can witness anything. It was there when the late heavy bombardment pummeled the inner planets 4 billion years ago. There when the first single-celled life emerged on Earth 3.5 billion years ago. There when those cells learned to photosynthesize. When they evolved into multicellular organisms. When life crawled onto land. When dinosaurs ruled and died. When mammals spread. When humans appeared and built civilizations and eventually looked up with telescopes trying to find planets they'd lost before ever discovering them. All of that happened while Planet 9 drifted through its slow, cold orbit, unchanged and unchanging, isolated and alone. But here's the thing about exile that makes Planet 9's story hit different. The planet didn't choose this. It was born in the inner solar system, close to warmth and light, part of the planetary family. Then something violent happened, and it got thrown out, banished to the edge, trapped in an orbit that keeps it forever distant from everything it used to know. It's like being flung so hard you almost escape gravity entirely, almost achieve freedom, but getting caught at the last second and sentenced to circle forever at the maximum possible distance, never quite free, but never able to return home either. There's something profoundly sad about that. If we're allowed to project human emotions onto planetary bodies, Planet 9 didn't ask to be where it is. It's not there because it belongs there, or because that's where planets naturally form. It's there because of violence, because of gravitational chaos, because of bad luck billions of years ago. And now it's stuck, completing its endless orbit through darkness and cold, so far from the sun that it barely qualifies as part of the solar system at all. Of course, this assumes Planet 9 exists, and this origin story is correct. The math suggests this exile narrative is likely, but we don't know for certain. Maybe the planet formed where it is now, out in the cold from the beginning, though that seems less probable given what we know about planetary formation. Maybe it got captured from interstellar space, a rogue planet that wandered too close to our solar system and got trapped by the sun's gravity. Maybe it's not a planet at all, but something else entirely. Which brings us to some truly unsettling possibilities. But if the exile story is true, if Planet 9 really is a refugee from the inner solar system that got thrown out billions of years ago, then it serves as a reminder of how violent and chaotic planetary systems can be. We look at the solar system now and see order. 8 planets in roughly circular orbits, everything stable and predictable. But that stability came at a cost. Other planets got ejected. Planetesimals got scattered. The early solar system was a demolition derby, and Planet 9 is one of the survivors, though survivor might be generous given where it ended up. So there it is, somewhere out in the dark beyond Neptune, if it exists at all, 5 to 10 times Earth's mass, frozen to near absolute zero, taking 10 to 20,000 years per orbit. So isolated that light takes half a day to reach it. So slow that watching it move requires the patience of civilizations. So dark that finding it demands searching through millions of data points, hoping to spot 2 pixels of light separated by decades. The planet that almost got away, but didn't quite make it. The world on the edge between bound and free. The exile circling in permanent darkness, belonging to our solar system by the thinnest thread of gravity, waiting 4.5 billion years for someone to notice it's there. But here's where the story fractures into genuinely unsettling territory. What if those 2 infrared detections, those aligned trans-Neptunian orbits, that perfect mathematical prediction, isn't pointing to a planet at all? What if something else is hiding out there? Something we don't have a comfortable name for? Something that shouldn't exist in our quiet, orderly solar system? The gravitational effects are real. The orbital alignments are real. The math is solid. But math tells you something massive is there, not what that massive something is. And the alternatives to a planet range from boring to cosmically horrifying. Option 1 is the scattered disk scenario. Instead of one large planet, maybe there's a collection of smaller bodies whose combined mass equals 5 to 10 Earths. Thousands or tens of thousands of objects, each one too small and dim to detect individually, but collectively creating enough gravitational pull to bend trans-Neptunian orbits the way we observe. It's the boring answer, the one that doesn't require rewriting textbooks or updating our count of planets. But the math doesn't really support it. Computer simulations show you'd need an implausibly specific configuration of objects, all arranged just right, all staying in formation for billions of years. Natural gravitational dynamics tend to scatter such configurations over time. The objects would interact with each other, with Neptune, with passing stars, gradually dispersing into a more random distribution. Maintaining the precise arrangement needed to mimic Planet 9's gravitational signature for 4.5 billion years requires either incredible luck or some mechanism we don't understand, keeping everything in place. Most astronomers who've examined this scenario conclude it's technically possible but highly unlikely. Option 2 gets stranger. What if it's not a planet or a debris field, but a primordial black hole? Let that sink in for a moment. A black hole, in our solar system, has been there the whole time. Primordial black holes are theoretical objects, created in the first fractions of a second after the Big Bang, when density fluctuations in the early universe were extreme enough to collapse directly into black holes without needing to form from dying stars first. These black holes could have any mass from microscopic to thousands of suns, depending on the size of the density fluctuation that spawned them. Most would be tiny, smaller than atoms but containing more mass than mountains. A few might be larger, containing 5 to 10 Earth masses, which happens to be exactly the mass range Planet 9 occupies. And here's the unsettling part. A black hole with 10 Earth masses would be about the size of a bowling ball. Maybe grapefruit-sized if you're talking about the event horizon, that point of no return where gravity becomes inescapable. Something you could theoretically hold in your hands, if your hands could withstand the tidal forces that would rip molecules apart. All the mass of 10 Earths, everything that makes up 10 planetary bodies, worth of rock and metal and core and mantle, compressed into an object smaller than a soccer ball. It sounds like science fiction. It sounds impossible. But physics allows it. General relativity predicts it. And if primordial black holes exist anywhere in the universe, which many cosmologists consider likely, then there's no particular reason one couldn't have been captured by our solar system billions of years ago. The sun's gravity doesn't discriminate. It pulls on black holes the same way it pulls on planets. If a primordial black hole happened to wander through the early solar system at the right speed and trajectory, it could have settled into an orbit just like any other massive object. The gravitational effects would be identical to a planet. 10 Earth masses of black hole pulls on surrounding objects exactly the same way 10 Earth masses of rock and ice would. The trans-Neptunian orbits would align the same way. The mathematical models would predict the same location. There's no way to distinguish a planet from a black hole by gravitational effects alone. You need to actually see the object. detect light reflecting off its surface, or heat radiating from it, or some other electromagnetic signature. And black holes, famously, don't emit light. They're perfectly dark, perfectly invisible, detectable only by their gravitational influence, or the behavior of matter falling into them. A primordial black hole in the outer solar system wouldn't be dangerous, not at those distances. You'd need to get within a few meters of the event horizon before tidal forces became lethal. But it's the conceptual horror that hits hardest. The idea that reality could contain something so alien, so removed from ordinary experience, so fundamentally wrong in how it relates mass to volume. A bowling ball that weighs as much as 10 planets. An object that breaks every intuition we have about how things should work. And it's been our neighbor for 4.5 billion years, circling out there in the dark. A hole in space, a rupture in the fabric of reality, a collapsed knot of warped space-time that used to be an depde, Arshasanden Arshidjofen, overdense region in the first microseconds after the universe began. If Planet 9 is actually a primordial black hole, then we've been living next door to a cosmic fossil, a remnant from the Big Bang itself, for the entire history of Earth and never knew it. Some astronomers have proposed ways to test this hypothesis. Black holes, even small ones, should have accretion disks if they're sweeping up any matter from the sparse gas and dust in the outer solar system. That infalling matter heats up as it spirals inward, emitting X-rays and gamma rays. So far, no one's detected such emissions from the predicted Planet 9 location, but the sensitivity required is extreme and the signal would be faint. Another approach involves looking for gravitational lensing, the way a black hole's gravity bends light from background stars passing behind it. Again, the effect would be subtle, requiring precise observations of millions of stars over years to catch the brief moments when alignment happens. The primordial black hole hypothesis remains speculative, possibly even unlikely, but it's not impossible. And that's what makes it unsettling. We've moved from there might be a 9th planet to there might be a hole in reality the size of a grapefruit containing 10 Earth masses lurking in our solar system. Those are very different statements, very different implications for what kind of universe we live in. Option 3 abandons exotic objects entirely and questions something more fundamental. What if our understanding of gravity is wrong? Modified Newtonian dynamics, or MOND, is a hypothesis proposed in the 1980s by physicist Mordechai Milgram. It suggests that gravity doesn't behave quite the way Newton and Einstein described, especially at extremely weak accelerations like those experienced at the edges of galaxies or solar systems. Instead of following the standard inverse square law forever, gravity might get slightly stronger at large distances and weak accelerations, enough to affect how objects move without requiring additional mass to explain the motion. MOND was originally developed to explain galactic rotation curves, the observation that stars at the edges of galaxies orbit faster than they should based on visible matter alone. Instead of invoking dark matter, invisible mass that makes up 85% of the universe's matter, MOND proposes that gravity simply works differently than we think at those scales. And if it works differently in galaxies, maybe it works differently in solar systems too. Apply MOND to the trans-Neptunian objects, and you might be able to explain their aligned orbits without needing Planet 9 at all. The objects aren't being pulled by an invisible planet. They're responding to gravity that behaves slightly differently at extreme distances from the Sunday. The math gets complicated, and not all versions of MOND successfully predict the observed orbital alignments, but some do. And if any version is correct, then we've been fundamentally wrong about gravity for 300 years. Newton's laws would need revision. Einstein's general relativity would need modification. Every physics textbook would require rewriting. Most physicists consider this unlikely. General relativity has passed every experimental test thrown at it for over a century. GPS satellites wouldn't work if our understanding of gravity was significantly wrong. Gravitational wave detections from colliding black holes match general relativity's predictions with extraordinary precision. But extraordinary precision, in some contexts, doesn't guarantee correctness in all contexts. Newton's laws work perfectly for everyday experience, but break down at high speeds and strong gravity, which is why we needed Einstein. Maybe Einstein's laws work perfectly for everything we've tested so far, but break down at extremely weak accelerations, which is why we'd need something else. If MOND or some other modified gravity theory is correct, the implications extend far beyond Planet 9. Dark matter, that invisible substance making up most of the universe's mass, might not exist. Galaxy formation models would need complete overhaul. Cosmology would face a crisis. It's hard to overstate how disruptive this would be to modern physics, which is also why most scientists are deeply skeptical and would require overwhelming evidence before accepting it. So we have three main alternatives. A debris field of smaller objects, which is boring but requires improbable configurations. A primordial black hole, which is terrifying but might not emit detectable signals, or modified gravity, which is paradigm-shattering but lacks support from other contexts. Each one explains the observations. Each one breaks something we thought we understood. And here's what makes the uncertainty genuinely unsettling. We can't just shrug and say, we'll figure it out, eventually. The answer matters. If it's a planet, that's fascinating, but not revolutionary. We add it to the count, study its composition and origin, update the textbooks with a new member of the solar system. If it's a primordial black hole, that's the first direct detection of such an object ever, proof that these theoretical entities exist, a window into the first microseconds after the Big Bang sitting right in our backyard. If it's modified gravity, that's a complete revolution in physics, potentially the biggest discovery since general relativity itself. Three possibilities, three radically different implications, and we won't know which is correct until we actually find the object, or definitively prove nothing is there, or accumulate enough evidence to distinguish between the alternatives. The math tells us something with 5 to 10 Earth masses is out there. The orbital alignments keep getting stronger with more observations. The 2 infrared detections suggest a specific location, but 2 pixels of light from decades ago aren't enough to tell us what we're actually looking at. Astronomers have proposed increasingly creative ways to search. Some want to use the Event Horizon Telescope, the global array of radio dishes that photographed a black hole's shadow in the center of galaxy M87, to look for gravitational lensing effects from Planet 9. Others suggest deploying space-based infrared telescopes specifically designed to scan the outer solar system. Still others want to use machine learning algorithms to comb through decades of archival sky survey data, looking for faint moving objects that human eyes might have missed. But the most promising approach is simply building bigger, better telescopes and methodically scanning the predicted region of sky, which brings us to the Vera Rubin Observatory, currently under construction in Chile. It's named after the astronomer who provided some of the strongest evidence for dark matter, though ironically, it might help solve a mystery that questions whether dark matter exists at all, if the modified gravity hypothesis proves correct. The Rubin Observatory will have the largest digital camera ever built for astronomy, 3.2 billion pixels. It will photograph the entire visible southern sky every few nights, creating a time-lapse movie of the universe showing anything that moves, changes, or appears where nothing was before. If Planet 9 exists and sits in the southern sky, the Rubin Observatory will find it. Not might find it, will find it. The telescope's sensitivity and coverage are sufficient to detect objects as faint as magnitude 24 or 25, easily bright enough to spot a Neptune-sized world even at Planet 9 distances. First light is expected in 2025, with full survey operations beginning shortly after. Within a year or two of operation, the Rubin Observatory will have scanned its entire survey area multiple times, accumulating enough data to track slow-moving objects across the sky. If Planet 9 is there, we'll know. If it's not there, or if it's in the northern sky where Rubin can't see, other telescopes will continue the search. But within the next few years, the uncertainty should resolve one way or another. And that's almost more unsettling than not knowing. Right now, Planet 9 exists in a superposition of possibilities. It might be a planet, might be a black hole, might be nothing at all. Schrödinger's planet, simultaneously real and unreal until we actually look. But soon we'll open the box. We'll point our best telescopes at that region of sky and see what's actually there. The mystery will collapse into an answer. What if the answer is a planet? We'll celebrate, add it to the list, study it intensively. What if the answer is a black hole? We'll rewrite cosmology textbooks and wonder what else we've been missing. What if the answer is nothing? We'll question our understanding of gravity and face an even deeper mystery about why trans-Neptunian orbits align the way they do. Every possible answer is unsettling in its own way. A planet means we were blind in our own backyard for centuries. A black hole means reality is stranger than we imagined. Nothing means our physics is wrong. There's no comfortable resolution to this story. Just different flavors of existential discomfort, different ways of realizing how little we actually understand about the universe we inhabit. And in the meantime, something is out there. Maybe. Probably. The math is too consistent. The orbital alignments too precise. The two infrared detections too well matched to theoretical predictions. Something with 5 to 10 Earth masses sits in the outer darkness, bending the paths of smaller objects, leaving gravitational fingerprints across the edge of the solar system. We just don't know what that something is. The ghost in the dark remains a ghost. Invisible, inferred, known only by the shadows it casts and the way things move when it passes nearby. But ghosts eventually get identified. We learn what's haunting us. And soon, very soon, we're going to flip the lights on and see what's been hiding there all along. On a mountaintop in Chile, 8,000 feet above sea level, where the air is thin and the sky is dark, a telescope is being prepared. The Vera Rubin Observatory. It's named after the astronomer who spent decades studying galactic rotation curves. The woman whose observations provided some of the strongest evidence for dark matter's existence, though she never won the Nobel Prize for it because the prize doesn't get awarded posthumously and she died in 2016. The telescope isn't remarkable for its mirror size. At 8.4 meters, it's large, but not record-breaking. What makes it extraordinary is the camera, 3.2 billion pixels. The largest digital camera ever constructed for astronomy. It weighs 3 tons. The sensor array is so large and produces so much data that a single image contains more information than the entire collection of images from the Hubble Space Telescope's first year of operation. This camera will photograph the entire visible southern sky every 3 nights. Not selected targets. Not interesting objects. Everything. Every star, every galaxy, every asteroid, every piece of space debris, every faint smudge of light that registers above the detection threshold. Then it will photograph the same regions again 3 nights later. And again 3 nights after that, for 10 years, creating the most comprehensive time-lapse movie of the universe ever made. Anything that moves will show up. Asteroids tumbling through the inner solar system, comets diving toward the Sunday, distant Kuiper Belt objects drifting along their orbits. And if Planet 9 exists, if it's in the southern sky where the Rubin Observatory can see it, the telescope will catch it. Not might catch it, will catch it. The combination of sensitivity, coverage, and repeated observations makes detection essentially inevitable if the object is there. First light is scheduled for 2025. Full survey operations begin shortly after. Within 2 years, the telescope will have scanned its entire survey area dozens of times, accumulating enough observations to track even the slowest moving objects. Astronomers will compare images, looking for faint dots that appear in slightly different positions between observations. Machine learning algorithms will help, flagging candidates for human review. But the process is straightforward. If something planet-sized is moving through that region of sky, we'll spot it, and then we'll know. After decades of speculation, after years of mathematical modeling, after filtering through millions of potential candidates and finding 2 possible pixels from archival data, we'll finally have a definitive answer. Planet 9 either exists or it doesn't. The uncertainty collapses. The mystery resolves. Except knowing brings its own complications. If we find a planet, the work only begins. We'll need to determine its exact orbit, which requires observations spanning months or years since it moves so slowly. We'll need to measure its brightness and calculate its size. We'll need spectroscopy to analyze what it's made of, what gases might exist in its atmosphere, if it has one, whether it's more like Neptune or more like a super-Earth or something entirely different. We'll need to understand how it got where it is, whether the exile narrative is correct, or if it formed there, or if it was captured from elsewhere. If we don't find a planet in the southern sky, Northern Hemisphere telescopes will continue searching. The Subaru telescope will keep scanning. Other observatories will join the effort. The search will expand and intensify until we've covered the entire predicted region. And if we search everywhere Planet 9 should be and find nothing, then the mystery deepens rather than resolves. We'll need to explain those aligned trans-Neptunian orbits some other way. Primordial black hole becomes more plausible. Modified gravity becomes more plausible. Or maybe we've been wrong about the statistics, wrong about the orbital alignments, wrong about the whole thing from the start. But here's what strikes me about this moment in the story. We're standing on the edge of an answer. The Rubin Observatory represents a threshold. Before it, we could speculate and model and search archival data. After it, we'll know. The technology exists. The telescope is being built. The timeline is measured in years, not decades or centuries. This isn't a mystery that will persist for generations. It's a mystery that will resolve in our lifetimes, possibly within the next 5 years. And that changes how we should think about Planet 9. It's not some distant, abstract problem for future astronomers to solve. It's happening now. The equipment that will answer the question is being installed. The software is being written. The survey strategies are being finalized. Somewhere, astronomers are preparing for the moment when they might see a faint dot moving through their images, a dot that represents the 9th planet, or a primordial black hole, or the first evidence that gravity doesn't work the way we thought. But regardless of what we find or don't find, the search itself has already taught us something profound. We don't know our own solar system. Not completely. Not even close. We've mapped the inner planets thoroughly because they're nearby and bright. We've studied the gas giants extensively because they're enormous and fascinating. We've sent probes to Pluto and beyond, but the outer reaches, the true edge, where the sun's influence fades toward interstellar space, remain mostly unknown, mostly unexplored, mostly mysterious. 400 years ago, Galileo pointed a telescope at Jupiter and discovered moons, proof that not everything orbited Earth. That observation helped overturn centuries of established cosmology. It was revolutionary. 200 years ago, astronomers discovered Neptune by noticing Uranus wobbling, proving that mathematical prediction could find planets before telescopes did. That was revolutionary in a different way, showing that physics could reveal the invisible. Now, we're potentially on the edge of another revolution. Not just finding a 9th planet, though that would be significant, but confronting the reality that our supposedly complete map of the solar system has always been incomplete, that we've been confidently describing our cosmic neighborhood while missing something enormous, that the inventory we thought we'd finished centuries ago still has blank spaces, question marks, objects lurking in the dark waiting to be found. And maybe that's the real lesson here. Not whether Planet 9 exists, not whether it's a planet or a black hole or evidence of modified gravity, but that we live in a universe where mysteries persist even in familiar territory, where the backyard holds secrets, where we're still explorers, still discoverers, still standing at the edge of the unknown, even when we think we've mapped everything. Think about what that means for everything beyond our solar system. If we can miss a 10 Earth mass object in our own neighborhood, what else are we missing in the broader universe? How many rogue planets drift between stars, invisible and uncounted? How many primordial black holes lurk in galactic halos, affecting galactic dynamics in ways we attribute to dark matter? How many distant solar systems have their own Planet 9s, massive worlds circling in outer darkness, pulling on smaller objects in patterns we'd never detect from light years away? The universe is bigger and stranger than we imagine, but that's always been true. What's new is the realization that strangeness isn't only far away. It's here, close, possibly orbiting our own sun at distances where we've barely looked. We got comfortable thinking we'd finished the local inventory, thought we knew how many planets we had, thought the only frontiers left were distant galaxies and exotic phenomena light years away. Planet 9, if it exists, says otherwise. It says the frontier is still here. The unknown still surrounds us. We're still at the beginning of understanding our place in the cosmos, not the end. And that should be exciting rather than unsettling, because being at the beginning means there's still more to discover, still mysteries to solve, still moments of revelation waiting in the data, in the telescopes, in the dark regions we haven't searched yet. The Vera Rubin Observatory will scan the southern sky. Other telescopes will scan the north. Machine learning algorithms will process the data. Astronomers will review the candidates. And within a handful of years, we'll have an answer. Not speculation, not mathematical models. An actual, definitive answer to whether a ninth planet circles our sun in the outer darkness. But here's the thing that keeps me awake. Regardless of the answer, we've learned something crucial. We've learned that we don't know, that our confidence was premature, that the map we've been following was always incomplete. And learning that we don't know is sometimes more valuable than learning what we thought we wanted to know. Because knowing what we don't know opens possibilities. It reminds us that certainty is often illusion, that the universe doesn't conform to our expectations. That reality is larger and stranger and more mysterious than the boxes we try to fit it into. Planet 9 might be real. It might be a black hole. It might be nothing. But the search for it has already revealed something true and important. We're still explorers, still standing at the edge, still looking out into darkness and wondering what's there. And soon, very soon, we're going to find out. So where does that leave us? Not us, as in astronomers or scientists. Us, you, right now, listening to this story about a planet that might exist, a ghost that leaves footprints, a mystery hiding in our own backyard. You're on Earth, third rock from a medium-sized star. In a solar system we're still mapping, in a galaxy we've barely explored, in a universe we've only just begun to understand. And somehow, that's okay. That's more than okay. That's beautiful. Because here's what Planet 9, real or not, actually teaches us. Not facts about orbital dynamics or gravitational influences. Something deeper. Something about what it means to exist in a universe that still holds mysteries. What it means to be small. What it means to not know. We spent centuries building up our confidence, mapped the planets, calculated their orbits, kicked Pluto out because we thought we'd finished counting and needed to clean up the definition. We looked at the solar system and said, this is complete, this is known, this is settled. We moved our attention to distant galaxies, black holes, the cosmic microwave background, exotic phenomena billions of light years away. We treated our local neighborhood as solved, finished, no longer interesting. And then someone noticed small rocks moving wrong, noticed orbits aligned in patterns they shouldn't follow, ran the math, and realized something massive might be hiding in the outer darkness, something we'd missed for 4.5 billion years, something that was always there, always pulling on things, always present but never seen. That discovery, or potential discovery, doesn't just add a planet to the count. It changes how we should think about knowing, about certainty, about the difference between what we've observed and what exists, because the universe doesn't care about our confidence. It doesn't adjust itself to match our textbooks. It exists independent of our understanding, proceeding according to its own rules, containing objects and phenomena we haven't found yet and might not find for centuries or millennia. Every time we think we've finished the inventory, reality reveals another layer, another blank space on the map, another mystery we didn't know we were missing. And that's not a failure, that's the human condition. We're pattern-seeking creatures living in a reality far larger than our pattern recognition evolved to handle. We build models, create maps, develop theories that work beautifully within certain boundaries. Then we push beyond those boundaries and discover the models were incomplete, the maps had edges, the theories need revision. Not because we did something wrong, but because the universe is genuinely bigger than any model we can construct. Planet 9 embodies that beautifully. The math is solid. The orbital alignments are real. The gravitational fingerprints point to something massive. But we don't know what. Planet, black hole, modified gravity, or something we haven't thought of yet. The evidence supports multiple interpretations, and we won't know which is correct until we actually see the object or definitively prove nothing is there. We're stuck in uncertainty, caught between what the data suggests and what our telescopes can confirm. And you know what? That's fine. That's good, even. Because uncertainty means possibility. It means discovery is still happening. It means we haven't reached the end of interesting questions. The day we answer every mystery is the day we stop being human in any meaningful sense. Curiosity defines us. Wonder defines us. The capacity to look at aligned orbits and say what's causing that, and spend years or decades chasing the answer defines us. Planet 9, real or not, gives us something to chase, something to wonder about, something to sharpen our telescopes and mathematical models against. Think about the scale of what we're attempting. We're looking for an object 5 to 10 times Earth's mass, which sounds enormous until you realize it's orbiting 20 times further out than Neptune. 20 times 4.5 billion kilometers. The distances become incomprehensible. Light takes 13 hours to reach there. The sun appears as a bright star rather than a disk, and we're trying to find a dim, dark, slowly moving object in that vast region of space using telescopes on Earth or in near-Earth orbit. It's absurd. It's audacious. It's maybe impossible. But we're doing it anyway. Filtering through millions of archival images, building bigger cameras, running increasingly sophisticated computer simulations, dedicating years of telescope time to scanning empty sky on the slim chance that a faint dot might appear in slightly different positions between observations. We're hunting ghosts with math and persistence, and the stubborn human conviction that understanding is possible if we look hard enough. That's what separates us from every other species on this planet. Not our intelligence, exactly. Not our tool use. Our insistence on understanding, even when understanding requires decades of effort with no guarantee of success. Our willingness to point telescopes at apparently empty regions of sky because math suggests something might be there. Our capacity to care about questions that have no immediate practical application, no survival advantage, no benefit beyond knowing. Why does it matter if a ninth planet exists? It doesn't, really, not in any direct sense. Finding it won't cure diseases, or solve climate change, or feed hungry people. It's pure curiosity, pure desire to know what's true, to complete the map, to answer the question simply because the question exists, and that's beautiful. That's what makes us human, not our answers, our questions. Planet 9 might orbit out there in the cold and dark, completing its 10,000-year lap around the Sun, pulling on trans-Neptunian objects, leaving gravitational signatures for us to find. Or it might not. Maybe we're chasing a statistical artifact, a pattern that isn't really there. Maybe the orbital alignments are coincidence after all. Maybe we've fooled ourselves with selection bias and wishful thinking. But either way, the search itself matters. Because the search is how we learn what we don't know, how we discover the edges of our maps, how we find the blank spaces that need filling. Every telescope scan, every computer simulation, every analysis of archival data tells us something. Maybe not here's the planet, but here's where we looked and what we found, and what that implies about what might be elsewhere. Science isn't a steady accumulation of facts. It's a conversation with reality. We propose ideas, reality responds. We adjust our ideas based on the response. Sometimes reality says, yes, that's correct. Sometimes it says, no, try again. Sometimes it says you're asking the wrong question entirely. Planet 9 is part of that conversation. We propose that something massive is hiding beyond Neptune. Reality is about to respond via the Vera Rubin Observatory and other telescopes. And we'll learn something regardless of what the response is. If the response is yes, here's your planet, we learn that our solar system is larger and stranger than we thought. If the response is no, there's no planet, we learn that reality is even stranger than a missing planet would imply. Either way, we learn. Either way, the conversation continues. And that brings us back to you, right now, on this planet, in this solar system, at this specific moment in human history, when we're on the edge of answering a question we only thought to ask a decade ago. You exist in a universe that still surprises us, that still hides things from us, that still contains mysteries within mysteries, from the smallest quantum scales to the largest cosmic structures. We've learned a tremendous amount in 400 years of modern science. We've mapped the cosmos, decoded the genome, split the atom, photographed black holes. But we still don't know how many planets orbit our own Sunday. We're still counting, still guessing, still running computer simulations and filtering through archival data, hoping to find 2 pixels of light that might, maybe, possibly be the 9th planet. And that's wonderful. That's cause for celebration, not frustration. Because it means we're still at the beginning, still explorers, still standing on shores, looking outward and wondering what's over the horizon. The universe hasn't revealed all its secrets. Reality hasn't finished surprising us. There are still blank spaces on the map, even the map of our own neighborhood. You live in that universe. You're made of atoms forged in stars that died billions of years ago. You exist on a planet that's been around for 4.5 billion years. One planet among possibly 9, circling a star that's one of hundreds of billions in a galaxy that's one of hundreds of billions in the observable universe. The scale of that should be crushing. The insignificance should be overwhelming. You're one person on one planet, in one solar system, in one galaxy, in a universe so large that light from its edges takes 13 billion years to reach us. But somehow, that doesn't crush us. It expands us. Because we're the thing in the universe that asks questions about the universe. We're the way the cosmos examines itself. Carl Sagan said it best. We're star stuff contemplating stars. We're matter become conscious, aware, curious. And that makes us significant even though we're small. Planet 9, if it exists, doesn't know it exists. It orbits through the darkness, unaware and uncaring, just following gravity's pull like every other massive object. But we know about it, or think we might know about it. We've inferred its presence from how it affects other things. We've built telescopes to search for it. We've dedicated years of human effort to answering whether it's real. We care about questions that have no answer yet and might never have answers we can fully understand. That's what makes us matter. Not our size, not our power, not our technological capabilities. Our capacity to wonder, to look at aligned orbits and say something's causing that, to build cameras with billions of pixels because we want to see what's hiding in the dark, to spend decades searching for an object we're not even sure exists because the question itself is compelling. And maybe Planet 9 teaches us that being small is okay. Being insignificant in cosmic terms is okay. Because significance isn't about size or power or how much space you take up. It's about awareness, about caring, about asking questions and chasing answers and standing at the edge of the known, looking outward into the unknown. The solar system is mostly empty space. The universe is mostly empty space. Between the stars, between the galaxies, in the vast voids between cosmic web filaments, there's mostly nothing. But in the tiny, improbable regions where matter concentrates enough to form stars and planets, where conditions happen to be right for chemistry and complexity, consciousness emerges, awareness emerges, curiosity emerges. And suddenly, the empty universe has meaning, has observers, has someone asking why it exists and how it works and what else is out there. You're part of that. You're one of the conscious things, one of the observers, one of the questioners. And right now, in your time, during your brief window of awareness, humanity is searching for a planet that might be hiding beyond Neptune. Whether we find it or not, whether it's real or not, the search itself is beautiful. The question itself matters. So sleep well tonight knowing that somewhere, billions of kilometers away, in darkness, so complete, it makes midnight look bright. By comparison, something might be circling, has been for 4.5 billion years, will be for 4 billion more, patient, hidden, waiting to be found, or not. Either way, we're looking, we're wondering. We're standing at the edge of the known and reaching toward the unknown. We're small and insignificant and temporary and absolutely, perfectly, beautifully human, still counting planets, still making maps, still discovering that the territory is larger than we imagined. And that's enough. That's more than enough. That's everything.